Okay. So now I'll talk about lattice-based digital signatures, which is an application of the lattice stuff that we did. So I want to kind of maybe emphasize this, okay, because maybe it's not clear that there's not really any, hopefully, algebraic problems that will be introduced. That's kind of the whole goal, really, of provable secure cryptography, is to kind of not introduce new problems to mathematicians. Is say, look, we have a proof, you know, keep going. There's nothing to see here, you know, there's no, you're not going to find anything that wasn't already kind of known. I mean, yeah, sure, you can work on the lattice problem, try to find short vectors in these things, but there's not going to be anything new introduced by this scheme, right? The scheme is just a reduction, the breaking that's solving the old problem that you kind of already did. I mean, I guess the somewhat new math, like that comes up here, it may be there's some new problems itself that's sort of optimized. But in terms of cryptanalysis, I'm not sure. Okay, but so you know, having said that, I will try to sort of re-sketch the proof. And that's going to be the important part. There's going to be a proof. Okay, with, well, it's not good. The problem is it can't be too precise because just the definitions in cryptography take about a page each. So, you know, going to do precise things, you know, will never be done. So I'll have to, of course, be a bit careful. Okay, so the next goal is digital signature. So they are actually practical primitive that we use for public cryptography. Every time you have to authenticate something, you use RSA. So the thing is, I guess this digital signature, just think of a signature, what it should work, right? You sign something, and then nobody should be able to forge your signature. Everybody should be able to verify your signature, right? So that's the idea of digital signature. I'm not going to give the exact definition because I'm not really going to be, unless I was building a digital signature, I'll be building something else which has a black box transformation for digital signature. And this is, I guess, Jeff also did the same thing. And these are authentications. So let's get to digital signatures a little bit. At the end, I'll just show you the black box transformation. There's nothing new here. And I'll talk about authentication. Or maybe identification. So the idea here is that an identification scheme can become digital signatures using a black box. Some of them, the one I'm doing. The idea is you usually have a prover who has some secret key and a verifier who has some public key which is associated to the secret key. And the goal of the prover is kind of to talk to the verifier and convince him that, yeah, I really am the guy who has the secret key, from, you know, which public key everybody knows. So everybody knows the public key, and the public key crypto. So the prover is going to talk to the verifier, you know, and say, you know, A, B, you know, A, B, C, D. And at the end of the conversation, the verifier is going to say, yeah, okay, I'm convinced that you have the secret, that you are the guy you claim you are. And hopefully no one else can sort of impersonate you, right? So there's two properties you need, kind of soundness and completeness. Completeness says that the prover will be able to convince the verifier of his identity. And soundness says that, well, no one else can. And then we'll see how you prove these two properties. Okay, so this is sort of the canonical authentication scheme. For some reason it's called that. It has 3 moves. It always makes sense that the prover starts. Well, maybe not always. Anyway, so the first step is, for historical reasons, I guess, called commit. Then there's a challenge. And then there's a mistake. I guess it always makes sense that the last round should be the oldest. And then the verifier kind of computes some function of the public key, the commit, challenge, and the output is the challenge. And so you want that a valid prover is able to get the verifier. value to check, and the old fake prover should be able to. Okay, so having said this, I guess in cryptography, the important thing is the model of the attack model. So when I say that nobody except the valid prover should be able to get this guy to accept, I guess we have to first talk about what can the adversary do, right? The adversary can do many things, right? The obvious thing, the simplest thing he can do is just watch, right? So he can just watch many communications between the prover and the verifier, and at the end say, okay, I've seen enough, I think I'm able to score. Okay. There are other things he may be allowed to do, right? Stronger. He may be able to pretend he's the verifier, send some malicious challenges to the prover, right? Not really having to follow the protocol, and then have the prover doesn't really know who he's talking to, right? The prover will respond, and the verifier will say, well, and the adversary will kind of learn some response based on his challenge, and then, not do anything. But then he'll say, okay, now I'm ready. After seeing all these responses to my malicious challenges, I can break this. You can even have stronger models, stronger attack models, but we actually need to get, since the goal is to get digital signatures, we only need the weakest sort of security notion for identification, which is, it's enough that for the scheme to be secure when the adversary just watches the scheme. Okay, so this is, I guess called honest verifier zero knowledge, or passively secure identification schemes, many names for this thing. Okay, so that's the kind of the first part. Is what is the security model and how do we prove security? That's the first part. And so the scheme should be. So we're going to construct a scheme that's secure when the adversary just watches the interaction. Okay? So we're going to prove that if an adversary who only watches the interaction can then break the scheme, then we'll be able to solve some Somebody's problem, right? Okay, so now what is the underlying assumption? The underlying assumption will be something that so we're going to try to keep things simple. So let's recall the ring system. So I'm going to actually present a few schemes that kind of modify, kind of build on top of each other to sort of, hopefully I get to the most recent scheme that would be Crypto 2013. Will be presented. So the ideas are similar and they get more and more efficient. Okay, so let's recall the ring sys problem. We're always working the polynomial r equals zx mod x to the n plus 1, or n of power of 2. Okay, doesn't matter. And so the ring sys, the particular instance, we're going to have three polynomials, a1, a2, a3, random in R. The problem is to find short that's the hardest part about whiteboard stuff. Names for that. Okay, short R, R1, R2, R3, such that A1, R1 plus A2, R2 plus A3, R3 equals, and everything is going to be null. So it's mod Q and mod X. Okay, so sort of by the pigeonhole principle, you should be able to see that for a random A1, A2, A3, there should be R's that are approximately of norm, I don't know, cube root of Q, something. Right, so you just want the entropy of the R's to be bigger than the entropy of this ring. Right, and then by pigeonhole into something. Yep. Small integer solution. So here there are no integers. The R's have integer coefficients. It made more sense. Okay, so this is our problem, and it's hard. If you can break this problem, so short means, I don't know, let's just say short means less than square root of it. Okay, this certainly is. If you can break this, you can solve short. You can solve worst case problems in any ideal in this room. So like SVP. You can solve SVP in any ideal of this room if you can break this. You can find these short solutions for random AY. Okay, so quick observation. This is equivalent to, I'm just going to get rid of one of the A's, right? It's equivalent, it's also hard to find A1 R1 plus A2 R2 plus R3 equals 0. Do you see this? Why kind of making one of these the identity is also just as hard. Because with high probability, one of them, or at least with non-negligible probability, one of them is going to be convertible. So just multiply everything by the inverse. So A3 inverse, A3 equals 0, and so these are also round. Okay. Okay, so that's the reason. All right. So now I'm going to sort of build a scheme based on this problem. Okay, so let's do secret key is going to be short S1, S2. Let's actually say 0, 1, negative 1, 0, 1, S1, S2 in R. Okay, so S1 and S2 are going to be polynomials in R with negative 1, 0, 1 coefficients. The public key will be A in R, completely random, and T equals AS1 plus S. The hardness assumption will have 3. I'm just doing this, I don't know, I think it's the simplest way to just get the problem. You could actually make a slightly better hardness assumption with only 2, with 3. So. Okay. So now the scheme is the following. Pick Y from some distribution over R. Okay, and this distribution is going to be the main pick file distributed Y1, Y2 from some distribution. And kind of picking this right distribution is going to be the main sort of thing in the problem. Okay, so let's skip this for now. And then compute W equals AY1 plus 1. So Hubert sends this to the verifier. The verifier sends a random C, pick sparse, so it's kind of like in just sparse, C in R. So by sparse, I mean the L1 norm of C is small. Okay, send C. And the response is Z1 equals Y1 plus S1C, and Z2 is Y2 plus S2. And so we send Z1. Right? Again, this is not quite correct. How to make this correct is sort of the second major part of it. Really connected to the distribution. We'll talk about this later. And then to verify, this guy checked this verification function, F, right? He checks that norm of Z1, Z2 is small, and AZ1 plus Z2 minus GC equals. So, I mean, I'll just let you stare at this for a minute. So Norman Z1 and Z2 is small. It's going to be small because Y1 and Y2 are going to pick the distribution that's small. And S1 is short, and the L1 norm of C is small, so S1 times C is going to be small, and so adding these two together is going to be small. Okay. And this is just true from the way we construct it. If you want to just work it out for yourself, and go on the board. Okay. Great. So now, this scheme sort of just, we haven't talked about this yet, but it satisfies completeness. So somebody who has the correct secret keys can make the verifier. Now, the hard part is always where we secure. So we're going to try to show, and kind of not really show because we haven't picked the distribution yet. We won't be able to prove anything, but at least we'll see what is needed to have security. All right. So now, let's pretend there exists an adversary who can break this scheme. So he can watch many valid interactions between the prover and the verifier, and then at the end say, okay, I am ready, and I'm going to break the scheme. I am going to play the part of the prover, and you will accept it. Okay, so these are the two steps of this attack. All right, so let's see how we use this adversary to solve the sys problem, the ring sys problem. Okay. Well, it's going to be, well, the secret key, in the thing I'm going to prove, the secret key is not going to be really -101. I'll explain. This is sort of the optimized version. I'll explain. All right. So now, we as a challenge get A1, A2, and our goal, we get this, and our goal is to find small R1, R2, R3, such that A1, R1 plus A2, R2 plus R3 equals. Okay, this is what our goal is. So we're given these random A1 and 2, and we have as a tool an adversary who breaks this. So we set the public key A equals A1, T equals A2. And we tell the adversary, these are the public keys. Okay? So this is where a little bit of in order for the adversary to say, yeah, okay, I'll work, these actually this A and T actually has to be a valid public key, right? But over here, T was A times S1 plus S2. Here, T is completely random. Okay? So either this T really is completely random when you pick S1 and S2, or the adversary just cannot distinguish random from not random. Okay, so these are the two cases we can work in, right? Let's pretend, not to make any complications into basic ring sys, but this is not really -101, but S1 and S2 have enough, they're still small, and they have enough entropy for A comma T to be completely random in R squared. Right, so there's enough entropy in S1 and S2 so that AS1 plus S2, you need some leftover hash lemma type thing. It can work. Okay, if you don't want this, then it's fine. Pretend we're working with the ring LWE problem, where the adversary cannot distinguish AT random from AT equals A times smaller for it. Okay, so that's the ring LWE. Actually, things become more efficient because you're allowed to have -101 coefficient, whereas with ring sys, you have to do the All right. Okay. So we have AT. We give it to the adversary, but now notice something. We do not know the secret keys, so how can we possibly play this game, right? But remember what the adversary needs. The adversary only watches he only watches the game, an honest game. He does not really participate in it. So at the end, what he really receives are the transcripts. All he really sees are these three things, right? So that's all we have to give to him. And the whole trick is that we can give it to him in reverse order, or at least we can create them in reverse order. We cannot create it in this order since we don't know S1, but we can create it in reverse order if some things are satisfied. So we do not know the secret key though. So how can we possibly give him Z1 and Z2, right? Well, that's going to be one of the major requirements of the algorithm, right? Of what we'll need for security. Z1 and Z2 and C will have to be independent of the secret keys. Okay, this is sort of the key, the most important part of it, right? So in terms, if you can think of it in two ways. You can think of this, this being necessary for two reasons. If you think of it in terms of doing a proof, then you see that it's necessary in order to do the simulation. You need to be able to produce Z1 and Z2 without knowing the secret keys. If you think in terms of the attacks, you can kind of come to the same conclusion, saying that, look, if Z1 and Z2 kind of depend on the secret keys, then you may be leaking the secret keys. And then, you get all sorts of math problems out of it. Okay? So what we want to, so kind of, it's proof is, having a proof work is kind of a, very natural prevention to this attack. Right? So if you're going to do a proof, it's very natural that Z1 and Z2 do not leak anything about the secret. Okay? So it'll be very important to have this distribution D here be set to some way, and then somehow get Z1 and Z2 to be independent of the secret. So this is going to be the major thing I'm going to do, but let's pretend we're able to do that. I'll do that later, okay? Let's pretend we're able to do that. So we can output Z1, Z2, right? So that's part of the transcript. C is completely random, so we know how to output C. And now W, well, we don't need Y1s and Y2s, but we know what W is. We know that W equals this. So we just set W equals and we give this type of order triple to the adversary. We say, well, you want to see an interaction? This was the interaction. And it's perfect, and the distribution is perfect. It is exactly the same distribution as if you were doing it this way. Okay? Okay, so that's sort of step one of the attack. In the first step of the attack, the adversary gets to see lots of transcripts. And we provided it for him. We said, well, here are the transcripts, right? And we don't even need to know the secret key, right? It seems like cheating, or something is fishy happening, but no, it's not, right? We're not able to produce the transcript in this order, right? So if we were to play against the verifier, we have to send this first and then respond to the challenge, we're stuck. But if all you care about is seeing a valid distribution, we can produce it. Okay? So if an adversary is supposed to be able to break the scheme just by watching, well, he can watch this. He should be able to break it by watching these interactions. Okay, good. So so we saw this, and now the adversary who breaks the scheme should say, okay, well, now I'm ready to break it. Good. So here's the adversary, and here's us, me, I don't know, it's called simulator. Or, I mean, it's usually called the simulator, but I mean, to me, it kind of didn't make any sense. Let's just say me, that makes sense. Okay. So the adversary is ready to break. So he sends, in the first step, he sends W. So, okay, thank you. We send him C. This step, he sends Z1, Z2. So he's successful. So Z1, Z2 are both small and satisfy that. So you have A, we know we have the property AZ1 plus Z2 minus TC equals W. What are we going to do with that? Not much. But we now use a trick. one of the few one of the techniques in crypto. And the adversary is just an algorithm. I guess, who is it? Oh, no, it's okay. So the adversary is just an algorithm. Okay, so at this, he sent a W and he's waiting for a response. Presumably, C was not the only response he could have responded to correctly, right? So he's waiting for a response. He responded correctly to C. We just rewind the adversary back to the state where he was waiting for a response. And we send him a C prime, a random C prime, okay? Presumably, he should be able to respond to the C prime. So we send Z1 prime, Z2 prime. That also satisfies AZ1 prime plus Z2 prime minus TC prime equals double. So with some probability, if he was successful with probability a fourth, I don't know, here, well, he'll be successful with probability about a 16th here. And you can prove this formally, that it's really like that. Okay? Here it's important that C does not equal to C prime, right? And this is why the domain of C, of this challenge, has to be sort of big enough to not get a collision when you pick random C and C prime. Okay? So now that we have the two equations, now we have something. The problem was we didn't kind of know any equation for W. But now we can subtract the two and get A times Z1 minus Z1 prime plus Z2 minus Z2 prime plus T times C minus C prime, or C prime minus C. Doesn't matter. And do you see what happened? I mean, we solved this. We solved this problem. A1 times this plus T times this equals this. Okay, so that's sort of a proof of knowledge in some sense. We were able to extract something from an adversary. This is how we prove that somebody who can succeed in this identification protocol actually knows something, because we can extract some information from him. And we extracted this information by rewinding. And the information was a solution to this system. Okay. That what? Yeah, but I haven't shown how to get Z1 and Z2, right? Well, what do you mean T? T is not leaking. T is a perfect public key, right? Yeah, I didn't show why. What I didn't show was why this was a valid simulation, right? So in order for the adversary to actually succeed, we have to first give him a valid simulation, because if we start giving him invalid things in the first step, that doesn't have to work in the second step. Right? So yeah, these have to be valid. But I'm sort of explaining, given that this is valid, we will be able to solve this. Is that okay? All right. So now the main problem is, how do you get these to be independent of the secret key? And the answer is rejection set. Okay? Well, no, I mean, that's not true. There's lots of ways to do it. Okay? So one way to do it is, let's just pick y1 and y2 completely random in RQ. Okay? So therefore, z1 and z2 will also be completely random in RQ. So everything will work, but what's the problem? It's not small, right? I mean, the reduction works, right? And we will be able to find something that's equals 0, but this will not be small, and this will not be small. I mean, this will still be small, but that's still not hard. I mean, if these two are not small, this is an easy problem that you can solve just with Gaussian elimination. Okay? So the whole trick is how do you keep y1 and y2 to be small and yet have z1 and z2 not dependent on s, on s1 and s2. Right? Okay. So the tricks here is to use rejection sampling, and sort of all the improvements over the years, the sort of most significant ones came from improving the rejection sampling procedure. Okay, so let's kind of give the very first rejection sampling procedure, I guess circa 2009, or 2008 even. It was in my piece. But anyway, okay. So the first one is kind of the simplest thing possible. And this is actually what, I guess if you remember Jeff's thing, that's what he was talking about. Okay? So the rejection procedure that is going to look at each coefficient of zi independently. All right. So, yeah, they're small. Right, right. That's why we have a chance to keep z1 and z2 small. Okay, let's kind of before, so let me just write down what rejection sampling is, okay? Okay, so in rejection sampling is you want to sample from some distribution f. But you only have access to some other distribution g. Okay. So what can you do? Well, I mean, this was, I guess, I don't know, who was, well, maybe this is the right audience. Who was the first person to ever use, what was the first paper to ever use rejection sampling? Well, that's, yeah, okay, but that's what you said. It was in the Bible. What was the distribution that? Okay. How's that before the Bible? I think the definition of Bible is we can argue. Okay. Yeah. Oh, okay. So the Bible is 5,000 years. Yeah. So whenever people cook, that's what is the function? Whenever they were trying to use something to cook, and if it didn't work, they threw it away, and then they came back to it. So they tried to sample from delicious, yet they had access to random or something. So they sampled from whatever they had. Okay. But they want to sample from something edible, right? And they. Okay. So anyway, so there's, a simple procedure for this is you first, so step one, sample x from f, from g, and two, accept x with probability f of x divided by g of x times some constant. Okay? So who's the sounds French, do you know this guy? Buffon? all right. Well, maybe we should.
Go ahead.
Well, okay. Good. Okay. So anyway, so this is the procedure, right? And so now notice. Okay, what is this M for? Well, M is here to make sure that this second part is always makes sense, right? So you want f of x divided by mg of x to be always less than or equal to 1. Otherwise, it doesn't really make sense to just accept the probability bigger than 1, right? And it's easy to show as well that if this is always less than 1 for all x, then the probability of actually outputting the distribution of this procedure is going to be exactly f, and that's easy to show, right? Just g of x times f of x over mg of x, which is f of x over m. And the number of steps you need to actually output something is going to be exactly f. The expected value is going to be f. Okay? So I guess the idea for rejection sampling, you want to have if you want to sample f, you should try to get access to a function g that's kind of close to f, right? If you want delicious things, you don't start out with, I don't know, tree, I don't know, wood. Okay. All right. So this is rejection sampling, and so now what is the kind of rejection sampling? What is going on here? What are the functions here? So here we have some function. We pick, y1 and y2 from some distribution, and at the end we're outputting z1 and z2 from the distribution of. Well, let's just look at just one z1 and one y1, right? The other one is exactly symmetric, so it's easy to just consider all of it. Okay. So we're going to output z1 equals the y1, which was picked from this distribution, plus something. So it's shifted in some direction based on S and C. Well, C you know, S you don't. In some direction, it's going to be shifted, right? And the person who knows S, the actual valid prover, he will not know what's the C, right? So for him, the direction will also kind of be random. Okay? So there's going to be this new distribution Z is going to be distribution of Y shifted in some direction. But what you want to do is output some from this distribution, and this new distribution, this vector G, you want to output something that is independent of S. So our distribution F should be independent of S, right? This F is going to be the distribution of final distribution of Z that we have. Okay. So the simplest kind of thing to do is to look at each coefficient one at a time. So look at the infinity. So let's look at this. Let me just give you a one-dimensional example, and you should be able to kind of see what's going on. Let's instead of considering vectors or whatever, polynomials, let's just consider integers. Okay. So let's say we have some integer y that's in the range, I don't know, -10 to 10, and then we have s that's in -1, 0, 1. Just an example, right? So y is always picked randomly from this thing, and s is fixed to be the -1, 0. Okay? Then, what's the probability, for example, that, and let's say z is y plus this. So, forget this. Okay? So what's the probability, for example, that z is going to be 0 given that s equals -1? What's the probability, for example, that z equals 0 given s equals 1? Same thing, right? And, the same thing given s equals 0. Okay? So now, what about probability z equals 9 given s equals -1? The same. Okay, good. And s equals 1, same, and s equals 0, this. Okay, so what about probability z equals 10 given s equals -1? Yeah, it's 0, okay? Because there's no way that y could have been 11, okay? So anywhere between -9, and for -9 it's the same, and 9, if you see z is output here, you have no idea what was y, what was s. Okay? But over here, you don't know. You don't know anything. I mean, things are being given away. Okay? So the same thing. So now here, it's just a n-dimensional, I guess, 2n-dimensional example of the same exact thing, right? So you have the coefficients of S1C, right? They have some maximum norm. Okay? So let's call it right? So there's the norm of SC. Well, okay, there's some maximum here, okay? And it's going to be norm. So the max all SC of, right? And then, so you can choose Y1, right, to be from what? So let's call this. The idea is kind of what we want to choose the y. Let's b plus minus what? What is delta? No. I want the distribution of y, this d, right? I want it to be a uniform distribution between 1 and 1 in order to be able to do rejection sampling with some decent probability. So I'm going to want y to be from some range, and I'm going to want to accept y plus sc if z falls within this smaller range, right? Okay, so this is going to be, well, I guess we should give it, well, I'll tell you, okay? So it's like negative, let's say negative mb to mb. And this is going to be negative mb plus b and mb minus b. Okay? So where's this m coming from? Well, maybe this should be actually 2m, but it's coming from the fact that you want the rejection sampling, so you want to be able to accept with probability, some good probability for all the n possible things, okay? So now, if we pick our y from this range, and then we add SC, what's the probability we're going to end up in here? This is 0. What's the probability we end up in this range if we pick from this range and add SC? Yeah, something like that. Yeah, okay. So it's approximately like 1 minus 1 over n. Okay? It's this, the size of this divided by the size of this, okay? So I made it so it's 1 minus 1 over m. What's the probability that every, well, m, yeah, m, okay, I will use m and n. So, yeah, let's call it n to make it less confusing. Okay? So 1 minus 1 over n. For each coefficient, what about, and now how many coefficients are there? N. So the probability that we will actually output something is 1 over e. Okay, well, there are 2 of them, so 1 over e squared. And if we output this z, it's completely independent of s and c, even though we know c. All right? Really? Well, I'm not going to get to anything. But we started late. Huh? We started like 15 minutes. All right. Oh, okay. These whiteboard talks take time. Okay. So now the question is, how big are the vectors z? Because that's something we want to minimize as well. Because over here, the solution to cis depends on these vectors z. The smaller the z, the harder they are to find. Okay. So how big are z? Well, they're all about this big. Each coefficient is about this big, right? And there are n coefficients. So it's approximately, and b, let's say b, let's treat b as a constant. Because, yeah, it's basically small. Okay, so it's going to be approximately norm of z1, z2, L2 norm, let's just, is approximately n to the 1.5. Okay, so this is kind of the way, if you do rejection sampling in this way, this pretty simple way, the z1, z2 are going to be uniform in this range, and their length is going to be approximately n to the 1.5. All right? So, and then everything works. Okay. Questions about this? So now an interesting question is, well, what about reducing this size? Perhaps there's a better way to do rejection sampling. Perhaps there's a nicer way to choose your G, okay? I mean, these G's are always going to be some shift of this distribution of Y, but perhaps there's a better way to do it rather than looking at each component one at a time. Okay, so the first, I guess, result from, 2012 is, yeah, there is a better way to do it, and it saves about root n factor, asymptotically. So let's kind of remember this. We had norm of z is approximately n to the 1.4 for the first rejection sample. Okay, so for the second one, I guess we'll need some definition of, and I'm not sure why this is a better distribution. It just works. Okay, so the normal distribution. So let's define rho of sigma comma v. Just the normal distribution. Okay, so this is just an n-dimensional normal Gaussian distribution with standard deviation sigma centered at v. Okay, we don't care too much about real numbers. We really want to talk about just integers. So we define the discrete normal over the integers. We define it as rho v sigma x divided by okay. So we just divide by sum over all integers. Okay. So now my claim is that if we choose y1 and y2 from this distribution, the resulting z1 and z2 are actually going to be smaller. Okay? So we're going to choose our d, choose the y1, y2 from d sigma 0. So basically the normals centered at 0. And now the zi's are going to be the normal centered at s times c. Okay, so now our f of x, sort of, I guess I erased it. So our f of x is d sigma 0. And that's actually the distribution of y is going to be exactly the distribution I want for z. You may think, oh, maybe I want a smaller standard deviation, a larger standard deviation. It actually doesn't matter. In a high dimensional space, it saves almost nothing. It saves exponentially little to consider anything different and creates a lot more mess. And so GSC of x is just d sigma s. So this distribution that we get, we want this one, but we get y plus sc, which is exactly this one. Okay? And now what we want is we want f divided by g of m to be less than or equal to 1. Right? So we want d sigma 0 divided by d sigma sc of x, m, to be less than or equal to 1. Well, let's just move m up. Okay? So if m is bigger than or equal to this divided by this, we're good. Okay? So let's divide this by this. That's the nice thing about these Gaussians is that they're easy to divide, easy to work with, easy to divide. So when you divide this by this, just plugging everything in, you get e to the minus 2 sc plus norm of sc squared. Okay. So m should be this. M should be bigger or equal to this for all x. Notice that this is actually impossible, right? Because this x could be big, therefore, and you know, this could be negative, so this could be infinite. But the nice thing is that this x that is big is never going to happen, because you're sampling from g of x. So the probability of getting a very large x when you sample from a Gaussian is going to be exponentially small. So you can kind of cut on some x and say, look, this will never happen. So yeah, this rejection sampling will only work with probability 1 minus, you know, some 1 minus 2 to the minus 100. Okay, that's good enough. All right. So that's fine. But it's important to be able to estimate this length, right? And this length you can estimate, so you can prove that norm of x comma sc is less than or equal to, with probability about, you know, 1 minus 2 to the, with probability 1 minus 2 to the 100. Okay, this is less than or equal to 12 norm s, when x is chosen from f of x. What? I'm sorry? 1? No, I didn't. Okay. So what? Is the sigma? Oh, no, sorry. Thanks. Okay, so in order, so this guy is going to be exactly the rejection probability, right? So in order to be comparable with this, it was, z was approximately this much when we were rejecting with probability, we're accepting probability 1 over e, right? So to make this 1 over e, well, we have to set sigma to be equal to 12 norm of sc. If you just set sigma to be this, then this just becomes e to the m becomes e. Okay? So now, if sigma is 12 norm of sc, how big is x? X is going to be about square root of n sigma. So norm of z is going to be approximately root n sigma, which is, and this is a constant, this is our b, 12b root n. No, something is wrong. Yeah, I'm missing a square root. What is missing? No, sigma is 12. No, this is norm 2. That's norm 2. No, sigma, maybe sigma is root n? This should be root n. No, why? Oh, sc is root n. Yes. 12 norm sc, this is 12b root n times sigma, okay, which is approximately 12b. So in the second one, z is approximately 12b. Well, there was a b here too. So let's just say 12. Okay. All right. So we've reduced by a square root of n. All right. So now comes the new part from, I guess, 2013, is how do you improve this even more? So I guess the question is, can you pick a different distribution so that when you do a shift, it even better fits under RF, right? And I think the answer, or this is what I was thinking about, but the answer I don't think you can actually do. You can't do it. So turns out the answer was to slightly modify the scheme. Okay, so let me give some pictures for motivation. So here's our distributions, right? This is our distribution that we want. This is our f of x. These were the distributions that we could possibly get. The shifts of f of x, right? And we wanted to divide f of x by these guys so that the result is less than 1. Sort of a scaled version of f of x divided by this should be less than 1. Well, the problem is in the tails. And this kind of occurred here. The problem is that when you look at f of x and this guy is actually going to be the ratio between this and this is actually going to be quite large at the tails. And so, no, sorry, the other way around. F of x divided by this is going to be quite large at the tail. Both the same thing. But we really care about f of x divided by g of x. So that's what. Okay, so f of x divided by g of x is going to be quite large at the tail. So you're going to have to shrink f of x by quite a lot, and that's this factor m here, which is 12 sc whatever, to get, well, not, yeah, the standard deviation has to be quite big in order for this guy to be something that you want, okay? So really what you're paying the price for is in the tails. But what if you could, so this is the new idea, what if you kind of combine these two distributions together into one, right? Because this distribution is really great on the tails because it's actually bigger than f. And this distribution is really great on these tails because it's bigger than f. So what if you combine these two distributions? So this is like f of x plus sc, and this is f of x minus s, right? So now the new distribution that you want to consider is actually, so instead of minimizing this, which was, so this guy, which was really e to the minus x squared over 2 sigma squared over e to the minus x. Instead, you worked with this. You put 1/2 here. Right? So, well, I mean, you have to do the 1/2 because otherwise it's not going to be a probability distribution. You take 1/2 of this and 1/2 of this. So that's the new distribution. So now it seems like if you combine these two together into this bimodal Gaussian, right, that has two modes over here, then you should be able to get a nicer distribution. And actually the kind of the part that's going to be the biggest ratio is going to be not at the tails, because at the tails it seems like it's going to be much better, but it's going to be over here. And that fits much better. So if you actually evaluate this, like what is the result here? Here it was e to the minus, here it was this guy, and you had this horrible term here that kind of gave you this 12 norm of SC. If you do this, you actually get this part. Squared divided by 2 sigma squared divided by the cosh of XSC divided by sigma squared. Okay? But the cosh is always bigger than 1, so this is always less than or equal to just e to the SC squared divided by 2 sigma. And this is much better than this. But there's a huge problem, obviously. I mean, you know, you can't just pick any distribution you want. You actually have to be able to generate this distribution from your scheme. Okay? So how do you generate a distribution that's sort of a combination of this and this? Well, from the scheme, it's almost sort of evident. I can take maybe 10, 5 minutes. Okay. Okay, so what you do is you can pick a bit b from -1, 1, and then set z1 and z2 so now you get exactly this distribution. Except that there's now another problem, that the verification is no longer guaranteed to work, because this thing is a times y1 plus b So when will this ever equal W? Well, it'll equal W when B is 1, which is sort of our old scheme where nothing happened. But it will not equal W if B is -1. If B is -1, we basically will want W minus 2TC to be equal to W. Or in other words, we want TC to be equal to minus TC. And this can never happen mod Q, because T is not 0. Okay? So, well, it seems bad, but surprisingly the answer is, well, consider everything mod 2Q and set T equal to Q. Set T equal Q and do everything mod 2Q. But you can still get a reduction for mod Q. Okay, so what happens now? How do you set the public key and the secret key? You want in your public key A equals R and then Q. So now this is R2Q equals A times S1 plus S2 mod 2Q. Okay, how can you set this? Well, kind of the n-true way. You can do it many ways, but I think the most efficient one is kind of the n-true way. Pick your S2. Sorry, how do you pick your A? Right, well, A equals Q minus S2 divided by S1 mod 2Q. There's a way to do it mod Q as well, but I will get confused with the... Okay, so, you know, n-true kind of said that if you do this, it's going to look uniformly random. Well, we say, well, mod 2Q will look uniformly random, but like I said, you can base it on the n-true assumption as well. It's no problem. Okay. So this is how you would create the public key. A would be Q minus S2 divided by S1 mod 2Q. And now the proof of security will work exactly the same way. You do this, except T is now Q. Equals 0 mod 2Q. Which implies if C minus C prime is never 0 mod 2, you have A times Z1 minus Z1 prime plus Z2 minus z2 prime equals 0 mod. So you solved sys for A constructed in this way, mod q. And you can sort of solve solve sys. Basically, a sys challenge using an adversary who breaks this scheme. So that's sort of it for the scheme. So we implemented this. I mean, I think, after 3 iterations of rejection sampling, we said, okay, this is good. So actually, the results are quite nice. It's fast, so it's much faster than RSA, and the keys, the size of the sort of signatures and keys, which is always the main problem in lattice-based crypto, is actually also smaller than RSA. So I don't know. I guess we gave it a name. So yeah, we decided, okay, it's time to give it a name as well. I don't know. So it's a bimodal lattice signature scheme. So we called it Bliss. I don't know. It's a bit okay. So it's a bit of a presumptuous name, but it only exists because I wasn't brave enough to go with my first choice. Oh, 5 minutes is so we were gonna maybe I could what no that wasn't my first choice. It was bimodal ring signature scheme, which is Briss, which is another word for circumcision, which is a great name for a short signature scheme. but I was not brave enough. Yeah, that's what Alon told me. Yeah, I thought like the Israeli guy, did you find it great? It's like, no, in Hebrew it's Brit, so we don't get it. It's not funny. It's like, no, but in America it's funny. It's like, whatever. Anyway. Okay, so yeah. So that's, I guess an open problem is, so now just to explain this, z is now approximately n over square root of 2. So we kind of went down from this 12 to over root 2, and this makes a pretty big difference in terms of parameter size. And so this n, I don't think you can get rid of this n. I think this n, just based on what we currently know, there are many ways to do asymptotic schemes, and this n is always there. The constants and logs, yeah, get rid of them. That should be possible. And yeah, I think it would be nice to, I don't know, to somehow improve this. I mean, because right now I think we're really down to improving constants. There's really not much. I don't know, if you care about removing n's, yeah, sorry. I mean, if you can, it'll be amazing. But this will be a huge, huge breakthrough, regardless of practicality. You can remove this asymptotic and make it to root n or something like that. Okay.